Swayam Prabha. Digital India. Educated India.
Finally, we start talking about molecules, and in whatever time is left in this course, we will only talk about molecules. We start with a very simple approach, valence bond theory, which I think most of us would know at least qualitatively, and then we end with a very simple approach for pi electronic systems, that is Huckel treatment. So, whatever we discuss now is actually much simpler than what we have developed so far while discussing atoms, and it seems that way because while discussing atoms we have built all the tools that we need to discuss molecules. Okay? That is why it is going to sound much simpler. So, here goes. We start with valence bond theory of homonuclear diatomics, and we get to know how is it that these atoms come close together and are very happy to be with each other, even though we have these big fat positively charged nuclei which repel each other strongly. What is the reason for stabilization when these nuclei come together enveloped by the electrons, and how are bonds formed, how are molecules formed as a result, and that is what leads to everything in this universe. So, there are two approaches to talk about this. One is valence bond theory and the other is molecular orbital theory. We start with valence bond theory. This essentially is an extension of Lewis electron dot model that everybody has studied in high school, right. Remember, we used to put dots for electrons and then we used to share, and we used to say that there has to be this stable octet and so on and so forth. Valence bond theory translates this very simplistic model of Lewis, Jane Lewis, in language of quantum mechanics, that is all. So, it is very simple to understand, and it is it relies completely on overlap of atomic orbitals and sharing of electron pairs. That, as I said, it is just a translation of Lewis theory into quantum mechanical language. So, atomic orbitals are retained with the modification. We are talking about many electron systems. Well, today we will talk only about H2, but then later on we want to talk about many electron systems. So, there you have to take care of things like shielding and all. In fact, as we will see, even for H2 you have to take care of shielding. So, atomic orbitals will be modified accordingly. So, actually it works fine for many systems, and the beauty of it is its simplicity. The problem of it is also its simplicity, because it is limited to 2-center 2-electron bonds. As long as you limit yourself to ground state of 2-center 2-electron bonds, it works beautifully. Problem is, the moment you go beyond 2 centers, or you have 1 electron or 3 electrons or more electrons, then it does not work. So, when you have more than 2 centers, you need to account for delocalization, which is actually not provided for in valence bond theory. So, you have to invoke this afterthought that is called resonance. Now, resonance is something that is absolutely favorite with students of chemistry. We know very well, we love pushing arrows, and we love talking about how a particular resonance structure is more stable than the others, but resonance really is not something that is built into VBT. It has been it is an add-on to extend the scope of the theory to delocalized systems. And even if you invoke resonance, there is something you cannot do, and that is you cannot access excited states. As we might have mentioned in the passing earlier, there is a lot of chemistry in excited states as well. Okay? All the photochemistry that you see, well, the very fact that you see, the process of vision, all that is something or the other to do with excited states, and valence bond theory is definitely limited to ground state only, nothing else. So, that is a very severe problem with valence bond theory. So, the way out is to use molecular orbital theory, in which you consider the electrons to move in the joint field of nuclei, and you set up the Hamiltonian. Well, we will set up the Hamiltonian for valence bond theory as well today. So, but then in molecular orbital theory, you set up the Hamiltonian, you can solve Schrodinger equation with this Hamiltonian exactly for H2 plus, and we will not even do it. But the moment you add one more electron, you encounter the usual complications that we got with many electron atoms, and we get more because now you do not only have more than one electrons, but you have more than one nuclei as well. So, what we do is we generate molecular orbitals, and I am sure you have come across this already. We generate molecular orbitals as linear combination of atomic orbitals, LCAO. So, if you remember what we had talked about earlier, we are actually synthesizing the wave function by using this orthonormal basis set of atomic orbitals. Okay. So, you can use variation theorem there, remember. The good thing about molecular orbital theory is that it is a general theory. It can handle delocalization just like that, you do not have to do anything special. It gives you excited states just like that, you do not have to do anything special. It is general theory, that is its advantage, and that is its disadvantage also. Perhaps I might seem like I am talking in riddles, because I said the same thing for VBT. What is advantage is also the disadvantage. I am saying the same thing for MOT. What is advantage is also the disadvantage, but it is true, that is how it works. Your advantage sometimes unchecked advantage can become a disadvantage, as we will see that sometimes it is a bit too general. It ionic structure of H2 for example is grossly overinterpreted if you use molecular orbital theory, but that will be the story for another day. Now you see let us write the Hamiltonian, and to write the Hamiltonian we will start with a hydrogen atom. Then even though your molecular orbital, even though valence bond theory has no scope for discussing H2 plus ion, we will write the Hamiltonian for H2 plus ion just because it has fewer terms, and then we will go on to H2 molecule. So, this is something that is very familiar to us, right. Ignore the picture for the moment, just look at the expression for Hamiltonian. Hamiltonian for hydrogen atom, something is wrong, yeah, hydrogen atom Hamiltonian, yeah, now you can, now in the picture is correct, sorry about goofing up there. So, hydrogen atom you remember nucleus and electron, okay. So, the Hamiltonian would be minus h cross square by 2 m a del a square minus h cross square by 2 m e del e square, where A stands for the nucleus or the atom as a whole, E stands for the electron in it, and minus q e square by R A gives you the potential energy for attraction of the electron experienced, the attraction experienced by the electron because of the nucleus. So, this potential energy, the first term here is kinetic energy of the atom as a whole, largely kinetic energy of the nucleus. This is the kinetic energy of the electron, and very soon we are going to write all this in atomic units. Okay. So, now what we will do is we will go in steps, we will add one more nucleus, one more proton actually, and we will discuss the case of H2 plus ion. Now, when we do that, all these 3 terms will remain of course, some more terms will come in. Which more terms will come? First of all, we will have a kinetic energy term for this nucleus B. We will have electrostatic attraction between this electron and the nucleus B. So, what we will have to write is we have to write something like minus q e square by R B for the potential energy term, and for the additional kinetic energy term of the nucleus we have to write something like minus h cross square by 2 m b del B square. Of course, do not forget M A and M B are one and the same, they are just protons. An additional term will come, and that is due to nucleus proton repulsion, that will be plus q e square divided by capital R, where capital R is the internuclear separation, right. So, this is the kinetic energy term for the second nucleus. Attraction, potential energy for attraction between the electron and the second nucleus, and this is the term for nucleus repulsion. Now, what happens if we want to go to H2 molecule, because remember valence bond theory has no scope for H2 plus, we have to talk about H2. So, we add one more electron, right. At the moment we add one more electron, we add many terms. How many more terms do we add? Whatever is there will remain, and moreover since there is a second electron, we have to use a little different nomenclature. So, what we should do is that instead of del E square, we have to write del 1 square, where 1 is the index of the first electron, and there will be another term minus h cross square by 2 m e del 2 square, okay, that is for the second electron. Then the second electron will also feel attraction with HA and with HB. So, now the distances will also have to be rewritten. So, this separation between the first electron and nucleus A, we will write it as R1A, separation between first electron and nucleus B will be R1B, between second electron and nucleus A will be R2A, and that between the second electron and nucleus B will be R2B, and accordingly we will get how many more terms? Well, we will get something like minus QE square divided by R2A minus QE square divided by R2B. This is due to attraction of this electron by these two nuclei. Nucleus repulsion is accounted for, and the other term that you have to bring in is, well, of course, kinetic energy of the second electron minus h cross square by 2 me del 2 square, and finally the additional term is electron repulsion. Electron separation is R12. So, that will be plus QE square by R12. So, I have shown you the additional terms that come in with respect to H2 plus Hamiltonian in highlights. Great. Now, of course, this is a very complicated situation, and we need some kind of an approximation before we can go ahead, and fortunately we have in our hands something called Born-Oppenheimer approximation, which essentially says that the total energy is a sum of all these energies. So, wave functions are all products of Hamiltonians and everything is separable. So, the statement of Born-Oppenheimer approximation, or the consequence of Born-Oppenheimer approximation that we will use here is this: when we talk about the electron, there is no need to worry about the nucleus. Nucleus is much more bulky, it takes much longer, its movement is in a different time scale altogether. So, when we do electronic calculations, we might as well take the nuclei to be stationary. This is extremely important. Okay. So, it is like something that is very light that moves fast, something that is extremely heavy moves slower. When we talk about the motion of the light particle, we do not have to worry about the motion of the heavy particle, that is all. So, when we use this consequence of Born-Oppenheimer approximation, how does this expression for the Hamiltonian simplify? And to keep things very simple, I am working with the Hamiltonian for H2 plus. For H2 we will just add those additional terms. So, first of all, this del A square, will you agree with me that this becomes 0? Will you agree with me that del B square term becomes 0, because we are considering the nuclei to be stationary. So, there is no question of their kinetic energy. So, these two we can ignore under Born-Oppenheimer approximation. What else? If these are stationary, then this internuclear separation will remain constant for our calculation. So, capital R can be taken to be a constant, and we can perform the electronic calculation for a particular value of capital R, see what the energy is, then go back and do it for another particular value of capital R, see what the energy is, and we can plot energy as a function of capital R and see whether there is a minimum. If there is a minimum, then that is the happiest situation, and that separation capital R is your equilibrium bond length. Okay. So, it becomes very simple. All you have to work with now for H2 plus is this minus h cross square by 2 me del E square minus QE square by RA minus QE square by RB. So, life is simpler than what it is, and in fact you can using elliptical polar coordinates you can actually solve it and get wave functions. But we will not do it because again they will become useless the moment you go to H2. So, what we do is we actually use linear combination of atomic orbitals, as we will discuss later. But today let us think how we handle this H2 problem, hydrogen molecule, dihydrogen molecule problem by this valence bond theory. Okay. So, we start with the Hamiltonian for H2 molecule, more terms as we had said earlier. I am going a little fast here because see it is not all that difficult and we have discussed this many times. So, if there is a problem, please go back and just do iterations, I think you will be fine. So, this is our Hamiltonian, and we have said what these different kinetic energy and potential energy terms are. Everything is accounted for: kinetic energy of the electrons. We ignore the kinetic energy of the nuclei by Born-Oppenheimer approximation. We consider the electron repulsion. We consider electron nucleus attractions, 4 of them, and we consider nucleus repulsion, keeping in mind that we can keep capital R to be a constant. So, this is the Hamiltonian, and if we write Schrodinger equation using this Hamiltonian, this is what we get if we write in shortcut. Okay. Our purpose is to get an idea of wave function, our purpose is to make an estimate of the energy, and energy of course as we said a little while earlier, the energy is going to be a function of capital R, internuclear separation, remember that. Okay. So, the complicating factor here is that this R12 internuclear separation is not a constant. You might remember from our discussion of many electron atom that whenever you have more than one electron in the system, they move deviously, they like to avoid each other. But it is not as if their separation is always the same, it is not. So, we cannot really solve this directly. So, we need some some approximate solutions, and we know by now how to use approximation methods. Okay. So, we will start with a trial solution and see whether it makes sense. So, let us think what kind of wave functions we can think of for H2, and while doing that we are going to use the atomic orbitals that we are so familiar with to try and construct the wave functions of the molecule, the molecular wave function. So, and of course, we will do that using common sense by and large. So, let us think what happens when r equal to infinity. Now, when I say infinity I do not mean infinity, say 10 angstrom is sufficient to qualify as infinity for this atomic and molecular systems, because if you think of the potential energy between these two atoms, that becomes 0 asymptotically, but becomes close to 0 within say 10 angstroms of internuclear separation. So, at such separations which we can say roughly is infinity for all practical purposes, electron number 1 moves in the field of nucleus A, electron number 2 moves in the field of nucleus B. So, electron number 1 would reside in the 1s orbital of nucleus A, electron number 2 would reside in the 1s orbital of electron B. So, what would the wave function be? Wave function would be the product of psi A1 and psi B2. Psi A1 means electron number 1 is in the 1s orbital of electron A, of atom A. Psi B2 means electron number 2 is in the 1s orbital of atom B. So, A and B are the names of atoms, 1 and 2 are the indices for electrons. Okay. So, this is what it is when they are very far apart. Electron number 1 is happily blissfully ignorant about the presence of this nucleus B, and electron number 2 is happily ignorant of the presence of nucleus A. Now, what happens when they come close together? Let us say when the internuclear separation is close to equilibrium bond length, okay. Does not even have to be exactly equal to equilibrium bond length, close enough so that this electron experience that nucleus and the other way around. Then it is not sufficient to write the wave function as psi A1 psi B2, that is only one of the components of the wave function, we write it as psi 1. The other possibility is that electron number 2 might reside on in the 1s orbital of nucleus of atom B, electron number 1 might reside in the 1s orbital of atom A. Okay. So, that is the second possibility, and that would be the second term psi 2 that would contribute to the wave function psi A2 psi B1. Alright. What is the wave function then? The wave function would be capital psi is equal to C1 psi 1 plus C2 psi 2. We are going to evaluate C1 and C2 maybe in the next class, but we can actually make a sort of a guess that what C1 and C2 could be if we do not worry about normalization of psi. Can you think what I expect the ratio of C1 and C2 to be, or rather what do I expect the ratio of the magnitude of C1 and magnitude of C2 to be? Please think about it, we are going to come to that eventually, right. So, this is my wave function to start with. This wave function was proposed by Heitler and London, and so this is called Heitler-London wave function. Now, using this wave function we can write down Schrodinger equation H psi equal to E psi, and then the problem is to evaluate the coefficients and evaluate the energy. I hope you remember what we do when we have problems like that. Let me write Schrodinger equation. I will just write it in terms of H for now. H operates on C1 psi 1 plus C2 psi 2 to give me something. I will just call it E for now, C1 psi 1 plus C2 psi 2. Well, we have done similar things earlier. So, what we do is we left multiply by this psi 1 and integrate over all space. So, what do I get then? Integral psi 1 H psi 1, well, and C1 comes out, plus C2 integral psi 1 H psi 2 is equal to C1 E integral psi 1 psi 2 plus C2 E. I am taking E to be a constant on the right hand side because E is the eigenvalue, even though we cannot solve it and find it, well, it is there. So, we just take it out, integral, oh what did I do, sorry, first one is wrong, I got distracted a little bit. So, C1 E psi 1 integral psi 1 over all space. Remember, I am left multiplying by psi 1 and integrating over all space, okay. All are in this case because we are talking about 1s orbitals, C2 E psi 1 psi 2. Now, first thing is this is not equal to 0, okay. This is very important to understand. Why is this not equal to 0? Because see, first of all, your these are products of wave functions, and secondly we are talking about one 1s orbital of this atom and one 1s orbital of this atom. These two 1s orbitals are not mutually orthogonal. This is a concept where sometimes we get confused. Two orbitals or two wave functions of the same system, if they are not the same, of course they have to be orthogonal to each other, but of different systems they are not orthogonal. In fact, as we will see, we are going to get some new quantity out of all this, okay. So, this is what you get, and similarly if you left multiply by psi 2, what do you get? You get something like C1 integral psi 2 H psi 1 plus C2 integral psi 2 H psi 2 equal to C1 E integral, I just write psi 1 psi 2 because the order does not matter, plus C2 E integral psi 2 psi 2. We are going to evaluate all these. For now what we do is we call this H11, we call this H12. We have encountered these earlier, remember. We call this H21 and we call this H22. And with this we can rearrange the equation also. We can write something like C1, we will write here, multiplied by H11 minus E S11. I will call this S11. We have encountered these, have not we? This is S12 plus C2 multiplied by H12 minus E S12, and this way we get another equation also in C1 and C2. So, system of linear equations, we will get the secular determinant, and for a non-trivial solution that secular determinant has to be equal to 0. So, now let me show you that secular determinant. Here is the secular equation, okay. You remember what we had written a little while ago. We got this H11 minus ES1 as a coefficient of C1, H12 minus ES2 as coefficient of C2 in the first equation. In the second one, this was the coefficient of C1, this was the coefficient of C2. So, of course, this is your secular equation. Now we have to evaluate these integrals one by one. To do that, first thing we will remember is that we are using normalized atomic orbitals, and since we are using normalized atomic orbitals, S11 equal to S22 has to be equal to 1. Is that correct? Let us write. What is S11? S11 is equal to integral psi 1 multiplied by psi 1 over all values of r. So, that will turn out to be integral psi a1 psi b2 and the same thing. Now, I hope with all our previous discussions of atoms, it is not very difficult for us to see that this is really a double integral, one in coordinates of electron number 1, one in terms of coordinates of electron number 2, and I can write it conveniently as a product of two single integrals, one in terms of 1, one in terms of 2. So, I get psi a1 multiplied by psi b2 psi b2, very simple. And as these 1s orbitals themselves are normalized, we get that these are this is equal to 1, this is also equal to 1, okay, not very difficult to understand. In fact, I will just erase this. So, one thing is out of the way, S11 and S22 are both conveniently equal to 1. Okay. What is S12? S12 is integral psi 1 psi 2 over all values of r. So, I write down the expressions for psi 1 and psi 2, psi a1 psi b2 multiplied by psi a2 psi b1 integrated over all values of r. And remember this also has to be a double integral because there are two kinds of coordinates, one for 1, one for 2. This again factorizes into an integral in electron number 1, integral in electron number 2. Psi a1 psi b1 multiplied by psi a2 psi b2. Okay. Now, what is the meaning of psi a1? Psi a1 is psi a1 essentially means electron number 1 in the 1s orbital of atom A. Psi b1 means same electron number 1, but in a different 1s orbital, different atom B. So, this integral is not equal to 0, right. Psi A and psi B are not orthogonal to each other because they are orbitals of two different atoms A and B. This is something that we have discussed earlier. So, what we would say is, and of course, there is no difference between the two, the indices are different, but that is all. So, we call this S, we call this S, and we call this S square, and it has a name. S is called an overlap integral. Why is it called an overlap integral? Because if I just draw these 1s orbitals for you, hopefully I do not have anything here, so it is okay to draw here. Let us say this is where A is. Its 1s orbital is an exponential decay, and since we have drawn 3D plots in the past, I hope it is okay if I draw on this side also. Sorry that it has gone below. Let us see if I can correct this. Entire thing will go. So, this is your psi A, and let us say your nucleus B is here. For that we will use a different color. This is the 1s orbital. 1s orbital is an exponential decay, remember. Now think what is the value of this integral. The value of the integral at this point is of course 0 because it is a product of this wave function and this wave function. Here also it is practically 0. The only region in which this integral has non-zero values is this, the region in which both psi A and psi B have reasonably non-zero values. Well, values are actually, if you want to be very rigorous, they are non-zero everywhere because they become 0 only asymptotically. But here what we are saying is practically, I mean if it is 0.000001, that we take that to be 0. So, only in this region where both the orbitals have more or less good non-zero values, only in that region this integral will have non-zero value. So, this is a region of overlap, that is why the name is overlap integral. Okay. And it is not very difficult to see from what we discussed just now that overlap integral is going to have dependence on r, is going to be 0 at a very large separation, and for 1s orbital it is going to be maximum at separation of 0, capital R equal to 0, right. So, using elliptical coordinates one can work out, will not work out, it is given as a problem in Macquarie's book. You can work out an expression and the expression turns out to be an exponential decay in R, R here is internuclear separation multiplied by a polynomial in R. Okay. And when we plot this, this is the kind of plot that we get, and this is what we had expected qualitatively also, becomes 0 asymptotically, but as you come closer and closer and closer it becomes maximum. Okay. This is the variation of overlap integral as a function of internuclear separation. In the assignments we are going to have several such exercises where we will give you different kinds of orbitals and ask you to work out how overlap integral varies as a function of internuclear separation, and you will see you will not get this kind of a variation always, okay, but that you work out in the assignments. Now, we are back to what we are talking about. We have simplified a secular equation a little bit. This is how it was, remember, H11 minus ES11, H12 minus ES12 and so on and so forth. We have sort of taken care of the S's. We have said this S11 equal to S22 equal to 1. So, this term will become H11 minus E, this term will become H22 minus E, and we have said that S12 is equal to S square. So, this will become H12 minus ES square, this one will become H12 minus ES12, sorry ES square again. Now, here H12 and H21 are the same as we had said earlier, remember you can use turnover rule. So, we are writing H12 and not H21. Okay. So, here it is, we have got this concept of overlap integral, we have introduced it, and we have got this secular equation which is a little simpler than what it was earlier. Okay, we have made some advance. Next we want to evaluate the H11 integral. This is where we will start from in the next class.